In this session, we would be focusing on the fitting of longitudinal data. We would be extensively using the R package NLME and the function LME of the R package NLME to fit the models. We would be fitting models on orthodont data. We would fit 3 specific kinds of models. The first model is called the random intercept model, the second model is called the random slope model, and the third model is called the random intercept and random slope model. We shall also compare among the models to see which one is the best model among the 3. Also, we shall see what is the difference between the maximum likelihood estimates as well as the restricted maximum likelihood estimates in context to a linear mixed model. So, to start with, we are once again going back to our orthodont data. Just a very small recapitulation of the orthodont data. The orthodont data is on 27 children, 16 boys and 11 girls. For each of the children, the distance from the center of the pituitary to the pterygomaxillary fissure was measured, and this was measured at ages 8 years, 10 years, 12 years and 14 years. The focus was on the growth curve modeling of the distance, and the age variable was shifted by mean age. Now, what that means is we had the ages 8, 10, 12 and 14 years, but we created a new variable which is say age minus 11, which is 8 minus 11, 10 minus 11, 12 minus 11 and 14 minus 11 for all the children included in the data. So, the orthodont data frame is in R package NLME, and we do not have to download any other the data set from any website or something. Loading the R package automatically loads the orthodont data. The simplest thing that we can do is call the library NLME, that is library NLME, and then we can plot the orthodont data. And this time what I have done is I have given a layout equal to C16.2. So, what this particular command does is it produces the graph in a layout of 16 into 2, but since we have 27, so we have all the males. So, there were 16 males, so all the males is in one group and all the females are in one group. Now, generally from the first impression it comes out that the females are starting at a lower distance as compared to the males, and probably there is definitely individual level variation, there is between male variation, and there is between female variation, and there is male female variation in the growth trajectory. So, the aim of this analysis is how do we completely model the data. Now, to do this, we start with the simplest analysis. We start by fitting a simple random intercept model. So, here what we have done is we have a mean model for the population, and for the individual variation we have just introduced a random effect at the slope level. Now, what is the mean model that we have used? So, we have used distance explained by age minus 11 into 6. What does that mean? That means we are fitting a intercept or a fixed intercept, but this fixed intercept is one for males and one for females. At the same time, we are fitting 2 slopes, one is for the females and one is for the males. So, that means we are saying that there are basically 2 growth trajectories, one trajectory is for the male and one trajectory is for the female, and each trajectory is linear in nature. So, we have a intercept for male, we have a intercept for female, we have a slope for male, and we have a slope for female. And also we are saying that the slope for random males and the slope for random and the slope for intercept for males and the intercept for females are varying, and this variation is due to the fact that the subjects are different, but this variation is only at the intercept level and not at the slope level. And how do we specify this? So, the main function to do this is the lME function. So, here we say lME distance explained by I age minus 11, that is the time variable, into sex. So, this ensures that we have a sex time interaction both at the slope level as well as the intercept level, and we specify a new thing which is random equal to explained by one given subject. So, that means we have an intercept. So, 1 stands for intercept. So, we have a random intercept per subject and the data is orthodon data. We can extend this. So, keeping the same mean model, we can extend this and say that random is I age minus 11 minus 1. What does that mean? That means we are now including a random effect for the time component, which is I age minus 11. But if we only specify I age minus 11, then by default the intercept comes in. So, we need to explicitly specify minus 1 given subject, data equal to orthodon. For the third model, which is a random intercept and random slope model, so we exactly use the random slope modeling, but omit the minus 1 part. So, by default, as I said, that here by default the intercept a plus 1 is there. So, I can either explicitly write it, or even if I do not write it, the intercept remains. So, lME 1 is a random intercept model, lME 2 is a random slope model, lME 3 is a random intercept random slope model. And for all the 3 models, the mean model has the same structure. So, the first model says that the variation is only due in the intercept of the subjects. The second is saying that the random effects is only due to the slope, and the third is saying that the random effects are present both at the slope level and at the intercept level. And we use 3 objects lME 1, lME 2, lME 3 to respectively store the 3 models. Now, let us start with the fixed effects. So, whether the 3 models gives the same fixed effect or not. So, we have used the library TextReg. So, TextReg is a nice facility which allows to see the model parameters in one table, and then what we have used is here. So, intercept I age minus 11 sex female and I age minus 11, this means I age minus 11 colon sex female means the interaction term. Okay. And so, what do we get? So, for all the 3 models, we see that the fixed effects are more or less same. The standard errors are also the coefficient, the significance is same, but the standard errors are different. Here, for example, the standard error is 0.49 and here the standard error is 0.28. So, let us interpret the model. The model says that the default is the level male. So, in general, the distance for the males is 24 plus 0.97 plus 0.78 into age minus 11. So, that is at the population level. For female, what happens? subtract minus 2.32 from 24.97. So that is the intercept. So here what happens, sex female gives the difference of the intercepts. So then it would be 24.97 minus 2.32, which is like 22.65, and the growth rate also is much lesser than the male. So for males it is 0.78, while for females we have to subtract minus 0.3 from 0.78 and we get it. But note that whatever is the mean model, there is no difference among the fixed effects, or no large difference among the fixed effects. So one way of seeing which model is good is by comparing the EIC criteria. So EIC criteria is telling us that 445.76. Now the idea is that lower is the EIC, better is the model, and EIC and BIC and log likelihood, all of them are telling that the first model or the random intercept model has the lowest EIC. A nearby value of the EIC is the random intercept random slope model, similar for BIC, similar for log likelihood, but the random slope model is definitely not the best one. Now some observations. Now by default LME computes the REML estimates. LME does not compute the ML estimates unless and until we specify it to compute ML. There is not much difference among the fixed effect estimates, that is true, and random intercept random slope models have produced slightly smaller estimates, although I have presented here the output rounded up to 2 digits. If somebody uses summary LME1, summary LME2 and summary LME3, then this feature can be easily understood. Now what about the variance covariance? So this gives me the Varkor function. So Varkor function is a function which expects a LME object and extracts the variance covariance. So for model 1, which is a random intercept model, it says that the random intercept is roughly 3.3 or 3.29, has a variance of 3.29, and the residual is 1.92. While for the second model, that is the random slope model, so we expect a randomness at the slope level. So that is why we have I age minus 11, and the variance is extremely small, meaning that the estimate, there is no variability at the slope level. So all the variability is mostly coming from the intercept level, and this is been confirmed by the random intercept random slope model. So if we use the random intercept random slope model, we see that the variability or the variance for the intercept is 3.35 and at the slope is 0.03. But remember that this here we have two random effects, B0i and B1i. So here for B0i and B1i, the correlation value comes out to be 0.206. So that means intercept and slope is positively correlated, meaning or mildly positively correlated, because 0.206 cannot signify a very strong sort of an association, but they are definitely positively correlated, meaning that if the intercept is high, then the slope value is also expected to be high. Now I can get the predictions from the RANF function. So RANF LME object would give the random effects. Note that for the first model, which has a random intercept, the RANF would give one column of random intercepts. For the second model, which has a random slope, it would give me one column of random slopes or predicted slopes, And for the third model, the random effects would give me 2 columns of predicted random effects. So that means RANF LME3 1 and RANF LME3 2. So that means RANF LME3 1 is the random intercept from the estimated predicted from the third model, and RANF LME3 2 or the second column is the random slope from the third model. So what I have done here is I have just created a data frame object of all the random effects and have named them as M-09, that means model 1 intercept, M2S model 2 slope, M3I model 3 intercept, and M3S model 3 slope, and then I can just print all of them. So here I have just printed the first few. And so what we are getting is that for the only the random intercept, so if we compare this with this, we see that only random intercept is producing smaller intercepts than the only random than the random intercept random slope model. So here the intercepts are bigger, or the predicted random effects of the intercepts are bigger. Similar analysis for the slopes. So the random slopes are producing smaller slopes, smaller predicted random slopes than the model having both random intercept and random slopes. So what we can do is we can have a ANOVA of the two models. So analysis of variance LME3 LME1 gives me, this is model 1, so LME3 is my model 1 and LME1 is my model 2, and it gives me a p value of 0.5556, meaning LME3 is not significantly different from LME1. Notice that if I use LME2 and LME1 ANOVA, it doesn't give me the likelihood ratio test. This is the reason, because here the variance parameter here was nested. So here it had random intercept, here it had random for LME1 it had random intercept, for LME3 it had random intercept random slope. While for ANOVA LME2 LME1, one has a random slope model and one has a random intercept model. And since the two models are not nested in the variance parameters, that's the reason why it is providing the AIC, the BIC and the log likelihood, but it is not providing a likelihood ratio test. Also, if I just compare between this, the AICs, we find that LME1 is far better in terms of AIC because it has a smaller AIC. So the takeaway message is that the random effect random slope and the random intercept random slope and the random intercept models are not significantly different, and the random intercept model is is better than the random slope model. So we can conclude that the most of the variation is at the intercept level. There is not much variation in the individual slopes. There is not significant difference between the random intercept and the random intercept random slope model, and the random intercept model is definitely better than the random slope model. So here we shall be going with the parameter estimates of the random intercept model. The reason being that the random intercept model is a easier model than the random intercept random slope model. So as I had previously said that we can by default the LME uses REML estimates, but we can make it ML using the condition method is equal to ML. So what I have done here is I have created another LME object which is exactly similar to the LME1 object, but here the method has been specified as ML. And then I have used screenreg list LME1 LME1 underscore ML. So these are the two methods, and REML and ML. So this produces exactly same fixed effects, and this is known because the fixed effects does not vary much for REML or ML estimates. But if we perform a variance covariance. So, if we extract the variance covariance, here we see that the variance covariance of LME underscore ML is 3.03, whereas the variance covariance for the variance for LME1 is 3.29. So, there is a difference in the variance estimate between REML and ML, but there is not significant difference between the fixed effects obtained from REML and ML estimates of the same model. So, in this session our focus was on fitting longitudinal models using the NLME package. We extensively used the LME function to fit the models. We fitted three types of models: the random intercept model, the random slope model, and the random intercept random slope model. We also used the ANOVA function to see which model is better, and use the predict function to get a prediction of the random effects. There are many advanced functions in the NLME package, like different variance for different strata. However, we have not used this because this is out of our scope. In the next session, we shall be talking about something called the marginal modeling strategy and the generalized estimating equations for marginal model.